Okay, thank you. My name is Carey King, and I'm going to describe some work that I've done here with Eric Kemp-Benedict on some long-term modeling and trying to integrate some fundamental aspects of the physical world and biophysical economics into a broader economic framework. And some of the goals for this type of model would be to explain if impacts of the finite Earth are having some sort of impact in the economic world. If we know the Earth is finite, there's disagreement on whether that matters or not, and if you put this concept into your economic model, could you tell whether it's having an impact or not? So that's sort of one of the drivers for this type of modeling. The future goals are to understand broad historical trends like a transition from agrarian to industrial. If we can understand from a basic modeling standpoint and be able to describe the agrarian to industrial transition, then we might have a much better basis to think about transitioning to renewables or low carbon energy supplies. That's going to be saved for some future work, but this presentation will focus on some results that explain some interesting trends and some things coming out of the model that can relate energy flows or energy consumption or resources consumption in general and economic trends such as investment and wages. And so that's what is going to be shown today. Now, to give you some implication of where this presentation is going to be going, this modeling framework, while not calibrated to any economy such as the United States, actually can tend to represent this very important trend of data in the United States. And this is showing that over the course of essentially the 1900s, the wage share was constant until the 1970s and then started a decline. And this has been a large part of discussion is what is the description behind this decline in the wage share, or the percentage of GDP that goes to pay wages. At the same time, there was another physical trend that changed at exactly the same time during the 1970s or early 1970s, and that was resource consumption per person was increasing up until this time and then went approximately flat. In this case, for the United States, energy consumption per person. So it turns out that the modeling framework I'm going to show you can sort of replicate this trend just by its inherent nature. And this is potentially a very powerful way or a very powerful argument and justification for using this type of biophysical approach. So what is the approach I'm looking at? The goal in doing this research was to essentially find the simplest model of two kinds I could and put them together. What is the simplest biophysical model? Something that has a population that depends on resources, and maybe there's a concept of physical capital. And then from an economic modeling standpoint, yes, sure, a population, but has a monetary version of capital, and it discusses wages and employment. Whenever you bring in wages and employment, you can now discuss something that has to do with distribution. And once you discuss anything that has to do with distribution, even if it's to two categories, you have a measure of structure. And so once you have a measure of size, how big is the economy, how much capital there is, and you have some metric of structure, you put size together with structure, and now you have a very powerful way to describe what's going on in the economy. If you neglect one or the other, you can describe a lot, but if you can put the two together, it turns out this is extremely powerful idea. So this is the research approach here, was to find the two basic models of these types and combine them together in a very fundamental, from-the-ground manner. What is the model showing? What are the flows occurring in the model, and how are they related? So there's three units in the model. There's a unit of nature and a flow of units of nature. This is generically resources. There's a flow of goods. These are things that are produced by a goods sector. So these turn out to be investment. They're investment goods and for household consumption. And there's units of money. So we're converting between physical units and units of money in a coherent way. Okay, what is the model doing? There's some nature out there as a resource. In the case of this simplistic model, nature is like a forest. It has a size and it has a regeneration rate. So nature here, it can be expanded to other ideas, but in this case, it's like a forest. What do you do with nature? You do four things with nature. One of the things you do is you operate capital that it does extraction. The job of this extraction capital is to extract nature. So it takes energy to produce energy concept. This is one of the fundamental ideas that you need to incorporate in a model to think about long-term growth and use of resources. A second thing that nature does is operate capital that does other things in the economy. In this case, it operates capital that makes goods, which turned out to be investment as one of the outputs. So these are like saying you need energy resources to run your factories, right? So this is rather obvious, but it needs to be included. A third thing that happens with nature is that nature sustains human population, or it's consumed by households. This is like people eat food, generically speaking. It could also be expanded to the idea that you use electricity in your house, but fundamentally this links to death rates in the model. And a fourth thing that nature is used for is to become new capital. So if you make an investment and you choose to allocate money, you have to extract nature to become that capital. The chairs you're sitting on are made out of resources from nature. This building is made out of resources from nature. So this says that's one of the fundamental things that nature has to become. You make an investment decision. This investment decision affects investment in new capital in each of the two sectors of this model. So you choose how much to invest in new goods capital, and you choose how much to invest in new extraction capital. And then finally, the goods sector, the output of the goods sector is physical goods. These goods become new investment, and whatever goods are left over become consumed by households. So in this model, I'm assuming that there is no specific consumption behavior. The investment behavior is defined, and consumption is just whatever's left over from net output, and that's what people consume. So that's how this model works. Okay, so what are the basics of the biophysical model that's behind this construct? This is derived from what was called the Handy model, the human and nature dynamics model made by a group at University of Maryland a few years ago. It's one of the simplest models you can find to explore these kinds of population and resource dynamics. They had 4 equations, two for population. I'm going to simulate it so that I only use 1 for population to make it even more simple. Population is births minus deaths. There's a nature component. It regenerates at some rate, and you extract it at some rate. And so the difference between that determines whether nature is increasing or decreasing in its stock in the environment. And then there is a notion of wealth here, which is really like a physical inventory of nature that you've extracted, but you haven't yet consumed. So that's like a physical inventory concept. Okay, so here's the equations, and I'll point out some of the important parts of this equation for nature. So there is something that says how big the world is. So if you want to explore if the finite world is having an impact, something in your model has to basically say this is how big I'm saying the world is, and whether it changes or not is up to you. So there is some size, there's some maximum resource size. There is a regeneration rate of this nature. If you wanted to model a fossil resource, you could put it as 0. But in this case, it can have some positive number. And there is an extraction or a production function, if you will, of the nature extraction sector. In their case, they were looking at an agricultural system. So their equation is some parameter, delta, some technological parameter you can play with. X are the population, the number of people that are available to do work, labor, and Y the size of nature. So I convert this, instead of making it only a function of people, it can be a Leontief, so it can be limited by labor or capital. So I expand that idea to include it into a more modern framework. And then another important feedback is the death rates. To make the model simple, the birth rates are assumed constant. In this case, the death rates are the only thing that change. If you do not consume enough nature per person in households, then the death rates increase. If you consume plenty of nature consumption per household, then the death rates can be smaller. So this is what regulates population growth. So what are the kind of results you get from a basic model like this, which is kind of the Lotka-Volterra structure? If you do not extract nature too quickly, then you can end up in this steady state condition. You basically extract resources at exactly the rate at which they regenerate, and you end up at a steady state population, and this is what the model can allow you to explore the conditions for this situation. If you extract nature at too high of a rate, well, then you will extract all of nature so fast that it does not have time to regenerate, and you accumulate too many people, and you deplete the resource base, and then eventually everyone dies. So this model allows you to play with this feedback, and that's a fundamental feature that is needed to really understand long-term growth and dependence on resources. But there's no wages, and there's no profits, and there's no idea of investment in this model. So how would you add that in the model? That's what the next trick was. Okay, so each sector, there's 2 economic sectors. There's 2 types of capital. Each one of them has some investment decision and accumulates capital. So this is just a standard investment minus depreciation framework for describing the accumulation of capital. And then there's a debt, or a private debt, for each sector. This is defined as the investment minus the profits of each sector. So if you invest more than your profits, essentially this is saying you get a loan from the bank to increase this investment, and this is debt increase. If you have investment that's less than your profits, then you reduce your debt, reduce your private debt. As already mentioned, the physical output of each sector is Leontief, so it's either limited by capital or limited by labor. In the results I'll show you today, there's no exogenous growth assumption in productivity of any kind, either for capital or for labor productivity, but there is an important endogenous feedback of productivity of extraction of labor, and that's this energy return on investment concept, so that's the key part of the model. So we have capital and capacity utilization, and this can adjust if labor is constraining, and this turns out to be a very important way to describe the long-term trends of the model. For the investment behavior, I take from some of the work of post-Keynesian economics and Steve Keen and some other papers that are in ecological economics by Gaël Giroud and Bovary. And essentially, investment is some proportion of depreciation. Are you going to cover all the depreciation of your capital or not? And some proportion of profit. If you want to invest more than profit, again, taking out a loan, then we can characterize this and see what the influence is, the rate of investment on the long-term behavior of the economy. And so I'm going to show you some results where this kappa 1, or this fraction that you invest relative to profit, is heavily influential in the results and help describe the modern trend that I showed you for the United States. So just to let you know about historical ratios of investment relative to profits, these two charts show the same data but shown in different ways. On the left chart is private investment divided by GDP, so what percentage of GDP is investment. On the x-axis is profits over GDP, so we can see the relationship between investment and profits. It's generally sort of a linear looking line, except there's two outlier times. The Great Depression and World War II are sort of outliers amongst this general bubble of where investment and profits tend to reside. On the right side is investment divided by profits and shown as a time series. And so the interesting things to point out here is if you did invest only equal to your profits, that would be investment over profits equals 1, which is this horizontal line. So we can see that in general, the United States economy invests 1.5 to 2 or 50% or 100% more than profits. The investment equals profits line is represented here as a diagonal. So we can see in World War II is a time when you were investing much lower during that time. In the Great Depression, the few years in the depths of the Great Depression are the time when profits overall for the economy were negative. So, but in general, in normal times, you're sort of investing in this 1.5 to 2 times profit range. So we can incorporate this general concept into the model. The final thing I'll describe about some of the basic theory behind the model is how you dictate wages. So we're using a sort of generic representation of a Phillips curve here. So this is just saying you can set some equilibrium point of employment and say if employment is above this number, in this case participation rate, so this isn't really employment like how many people are seeking to work, this is actually what the fraction of the population that's working is, what will be used in the model. If it's greater than this assumed equilibrium, then wages are rising. If it's less than this assumed equilibrium point, wages are going down. So that's explaining the rate of change of wages is just a function of the current wage and this other function. Okay, so now I'm going to describe this important feedback that's sort of the energy return on investment part of the model. And here I'm showing this sort of an input-output table formulation of the model where we have the two sectors and the intermediate transactions here. The net output or GDP portion of the economy is consumption, investment, and a change in the value of inventories. So since I'm tracking physical items and the value of these physical items, it turns out tracking inventory becomes quite crucial just to make the modeling work properly. And then the value added and wages and how wages and profits get distributed are described here in the value added sector. There's profits, wages, interest payments, so including debt, there has to be interest payments, and the depreciation of existing capital. All right, so what's the important feedback in this model? The results I'll show, these technical coefficients, these A technical coefficients, every one of them is constant. It has a parameter that's interesting to describe. In the model, every one of them is constant except for this AEE term, or the amount of nature that is required to operate the capital whose job it is to extract nature. So how much input of nature do you need to extract unit of nature is described here. So here's the production function of nature extraction, the delta parameter, a technological parameter to play with. How much nature is there? how much capital do you have, and what percentage is that capital being used. And then the numerator is, again, the capital times its capacity utilization, and then some parameter you can play with, which is this is how much nature is required to operate the capital itself, whose job it is to extract nature. And the important point here is that the units of nature in the environment are in the denominator. So as nature gets depleted and goes to zero, this term would tend to go to infinity, but in fact you can't go to infinity because once this reaches 1, this means that the nature extraction sector is using all of its extraction just to function itself, and there's nothing left over for the rest of the economy. So the limit on this is really 1, and this is sort of the physical energy balance, or nature physical balance, if you will, restriction in the model. Okay, not going to go into how prices are solved. We solve for prices in a couple ways with a lot of help from Eric here, figuring out and formulating how we can solve for prices. They're essentially a markup on the costs, so it's just some percentage increase on top of costs that's set what the prices are, and then we solve for prices of both sectors simultaneously. And just to be clear, the costs are the intermediate purchases of goods, cost of labor, interest payments on debt, and then depreciation. In the model, I'm going to show results for the assumption of which the markup is a constant fraction on top of costs. We also have one where it changes with profit rate, which has a completely different dynamic. So understanding these roles about how prices are formed in investment is, of course, very important. Okay, so just keep in mind the causal effects that are happening here in the model to interpret the results. First, sectors decide, each firm decides how much to invest in new capital. Then we figure out how much labor there is needed and what the employment rate is and how wages change. Once you knew this, you can see, okay, what's constraining? Is it capital or labor that's constraining the situation? If it's capital is constraining, then for the most part, things are fine. If labor is constraining, then we go through some other conditions I'll describe. We calculate the output, both the gross output and the net output of the economy. And then household consumption is effectively whatever is left over from net output, Y. Consumption is whatever's left over, and then that, again, is what impacts death rates and has an impact on capacity utilization. All right, so I'm going to show results for this constant markup assumption going forward. All right, so in describing several charts that have results, I'm going to tell you how to interpret them here. And there are two general trends that I'm showing, and it turns out there's effectively a threshold depending on how much the level of investment is that takes you from one dynamic behavior, if you will, to another. So it's this relative investment level of which most of the charts are going to show a difference. If you're looking at the dashed line, this is a relatively high investment level. If you're looking at the solid line, this is a relatively low investment level. And so the rest of the results will dictate, will explain that. So keep that in mind as I show every slide going forward. From here, we can see that the simulation results from the low investment level essentially reach a point and stop, and I'll describe that. So I'm just going to call this an infeasible point. This is if price investment's too low, and equivalently, if you set the price markup too low, you get the same general result. So in general, it's either a price or an investment level is too low, and the system is generally stable or quasi-stable at this kind of steady state condition, and you can go feasibly there if the investment level is high enough. Now, we did some investigation and said, okay, what's really the driver in going behind this? And what it turns out is the difference is whether you invest such that you put the participation rate at its maximum level, or whether you force the economy to go into a labor limiting condition or it stays in a capital limiting condition. And so that's what I'm indicating here. In this case, I'm assuming that profit is essentially 1.3 times, or investment is 1.3 times its profit and covers its depreciation, and you never reach the maximum participation rate, which in my case I just set at 80% in the model. But if you invest high enough, if you invest 1.5% or 1.5 times the profit and cover your depreciation, you reach the case of maximum participation rate. And this shifts a different mode in the economy. Now labor is limiting instead of capital is limiting. Okay, so one way to interpret this is if I'm in a low investment rate condition and capital is always limiting, I'm able to accumulate more people. Recall, if I'm extracting resources, the resources get distributed to 4 things. One is operating extraction capital, operating goods capital is the second, I can basically feed people, it's getting allocated to people, and it's getting allocated to make more capital. So if I'm slowing the rate at which I invest, there's essentially more resources that are extracted, left over for people, and I accumulate more people. So the peak here in the solid line is in the low investment case. The peak population is higher than the peak population as if I invest more or at a higher rate. If we look at the total amount of capital, which is on the left chart, in the dashed line there's a high rate of investment. The capital is always accumulating faster, sort of by definition of this assumption of the rate of investment. So the capital is accumulating faster. Because the capital is accumulating faster, there's left over for people, and the population doesn't grow as high. So if we look at the low investment case here, and we look at prices or the real price, the price of nature tends to rise sort of exponentially. It just keeps going up, but it doesn't go actually to infinity because we have this physical constraint. I can't extract all the resources, and that's what's shown here. So this is what I call the net external power ratio. This is usually referred to as energy return on investment, but I use the word power here because this is a function of the flow rate of nature. It's not a function of the stock of nature or the nature integrated over a long period of time. It's a function of the current flow rate of nature. So this is net nature extraction, which is what is the total rate of extraction of nature minus what the extraction sector needs for itself. That's the numerator, and then the denominator is just how much nature extraction does the nature sector need for itself. So if the net nature extraction is 0, this means that the nature extraction sector is using all of its own output, and that is what is shown in this graph. So it reaches 0, it reaches the point of 0. So in this case, the extraction sector is using everything it needs to operate itself and try to invest in new capital. And this is where essentially the system breaks down. Something would have to change if you met this condition, or something probably would change right before you meet this condition. So that's why the price goes up. The price goes up. This means the profit share goes up for the capital sectors, and the wage shares decline very rapidly, not shown here. So again, an important point here is here's nature. Here's again the chart I showed earlier. Here's the amount of nature that's in the environment. It does not go to 0. Right? So by having this feedback, this is essentially the rule that we all know, which you're not going to extract every bit of nature. You're not going to extract every drop of oil from the ground, because at some point it is going to become too expensive to do that, either from a physical standpoint or a monetary standpoint. And here I'm showing that these physical and monetary standpoints are linked together fundamentally, so you can think about it in either way. So this is kind of strange, or at least to me I thought it was kind of strange. If you invest too slowly, in some sense, you keep extracting and depleting nature even more than if you invested a lot. If I have less capital, somehow I seem to go ahead and try to deplete nature further than if I had more capital. This is kind of confusing, but again, it turns out to be a function of putting the economy into a labor-limiting condition. So we can debate whether that is the goal of capitalism, is to put the economy in maximum employment so that labor is the limiting condition. The more I look at the data, this seems maybe to be the case. So that could be part of discussion. So I'm going to go through the phases. What if you do invest in capital fast enough and you end up in this more stable condition? What are the phases of operation in the model? So I'm showing 3 things, and I go through step by step the different phases of the simulation, and it changes its mode of operation, if you will. And again, we're going to be paying attention to the dashed lines that are this high investment case. All right, so there's phase 1, or mode of operation 1, which is I'll call just normal operation. Capital is limiting, population's growing, capital's growing, we're increasing the extraction rate of nature, everything seems fine. This is what everybody wants to sort of have as the condition happening all the time. All right, so this happens. Capacity utilization is at its normal rate, which in this case is 85%, so everything's operating at its maximum level or its target level of operation, and everything's great. Okay. Then we get to a point where the economy is now limited by labor. I've invested in enough capital, but there's not enough people. I can't employ in this model 100% of the people, because some people are children and babies and old people, and they're not going to work. But I've now reached this labor limiting condition, and now the capacity utilization has to drop a little bit to account for this. I can't operate all the capital as much as I would like. So this starts to occur, and I need to reduce goods output to account for this. Essentially, the goods output of the economy starts reducing to account for labor as a limiting condition. Then I reach a slightly different condition. The economy is still limited by labor, but now I've reached a minimum threshold for consumption by households. So that's shown by the middle chart. So the dashed line here is nature consumption in households per person, and I set some arbitrary limit greater than 0. This is saying households have to consume some nature. If it was 0, they would all, in some sense, die instantaneously. It's like food. If you don't have food, you're all going to die. So I set some minimum level of household consumption per person, and in this phase 3, it has reached this level, and once it's reached this level, it now has to reduce goods output even further, and that is done by reducing the capacity utilization of the goods output at a higher rate, which is now the capacity utilization of goods is declining relatively rapidly. But this only lasts for a while in this model. The population starts to decline after this time because the death rates are relatively high, and the population declines. So then in phase 4, the household consumption of nature is above this threshold level, but I'm still in this labor limiting condition of the economy, and the goods output has to continue to decrease to be able to account for this. And the major difference now is on the right chart. This is the goods consumption by households, and we can see it really starts to decline during this time. So now the flow rate of nature, I've accumulated much capital. I'm still investing in more capital, but the idea is I have to operate it less and less, and the goods consumption, there's less and less left over for consumption of goods because I keep investing in more capital. So the households are taking the hit here. And then finally, there's a fifth condition here. I've gotten to the point where the goods consumption at households is 0. They can't have negative consumption, or at least I'm not modeling household debt in this moment, or a concept like that. So now the goods consumption is 0. Once this is done, again, because of the restriction of the flow of nature, now the investment in capital overall has to start declining, and the net investment, not shown here, in capital starts to decline. And so this is another phase of the economy. So these are kind of the difficulties or the things that you have to go through if you're going to really simulate a long term and try to understand what happens if nature is limiting the economy. You have to start making these decisions about, well, what happens when I meet these constraints and how would the economy adjust? I've gone through how I've discussed it here. It turns out it seems to be fairly reasonable when we compare it to the data. Okay, so here's where it gets interesting in terms of understanding the current situation. So we're looking at nature extraction per person on the right. It goes up, it reaches some maximum rate, and then it ends up as a rough steady state. The wage share is in the middle. What percentage of value added is going to wages? And then this is over here is representing the depreciation share. What share of value added is going to depreciating capital? So the interesting thing is there's this transition time that I'll mostly use defined by the nature extraction rate, right? There's a transition from a time of increasing nature extraction rate to one of roughly steady state nature extraction rates, right? This is energy transition or nature transition time. And during this transition time, the economy goes from sort of one general mode of operation, capital limiting, to another mode, labor limiting, if we're thinking about the dashed lines. So if we're in this high investment case, and we're looking at the dashed lines on these figures, there's a time of roughly constant depreciation share, roughly constant wage share, and increasing nature extraction rate. Then there's a transition time, and you end up in a time that looks different, which you have an increasing depreciation share. You just keep investing in more capital to make sure the economy stays in this labor limiting condition. The wage share is now taking the hit, so depreciation share goes up. Wage share is the thing that has to respond and go down, and this corresponds to a time of constant nature extraction in this case. Okay, so given that, does this have anything interesting to say about data in the real world? And this is the chart I showed at the beginning. This is the United States economy, data for wage share and energy consumption per person. And I've showed results from my model that I'm claiming actually can replicate this general trend, actually have this sort of fundamental basic trend in it. So I'm showing one of the results from wage share, which is the black line, and the nature extraction per person, which is the dashed red line to mimic the same colors on the left and right graphs. So we have a time period in which the wage share is flat or approximately flat in both models, and then declines at a more rapid but sort of generally steady or linear rate over time. So there's flat and declining wage share in the data and the model. and the resources consumption per person has a time which is increasing and then goes approximately flat. And these transition points occur at exactly the same time in the data and exactly the same time in the model, roughly speaking. So this gives me some confidence that this model is actually telling us something very important, and that by its formulation it can explain a very fundamental dynamic between economic outcomes and distribution, in this case just between wages and other aspects of the economy, and physical resource extraction itself. Again, there's no exogenous assumption of growth or anything in this model. So what are our takeaways? We can consistently track physical and economic flows, like many past ecological economics historians have discussed the need for. We've formulated a model that can do that, so we have a base model from which we can maybe refine and add components. There's no government in here. There's no renewable energy sector versus a fossil energy sector versus biomass, so we can explore those kinds of additions. There's no climate or atmosphere model. You could add this to make it into an integrated assessment type model concept. There's no Federal Reserve Bank. You can start to add all these other pieces, just like it's done in kind of the post-Keynesian literature. The model seems to explain a very important coincident trend in energy consumption and wages. So this would be good for discussion to see if anybody has seen anybody actually be able to recreate this from a ground-up model and explain that really important trend that's been happening since the 1970s and that the mainstream economists seem unable to explain. And it shows how economic decisions, say the rate of investment, can affect economic or physical outcomes. So this idea that the physical world is not independent of how we choose to use it, and that how we choose to use the physical world affects what we actually get from the physical world, or what our interpretation is of it. So that is the end of my presentation. Thank you very much.